Hello, my name is Youngseok Lee from Sungkyunkwan University. Today, I'm gonna present quantum computing with Ising Anyon. Here's today's contents. So I'm gonna first give you some introduction, and next, I'm gonna explain the quantum computing with Ising Anyon. And the last, I'm gonna conclude my presentation. So, what is an anyon? That we have to know boson and fermion first. uh, if there are two particles and if we try to change their location, a boson is going to have no phase change. But if the particles are the fermion, they're going to have the -1 phase. And if the particles are the anyons, they're going to have not +1 or nor -1 phase. So actually this comes from the topological difference between two dimension and three dimensions. So what is topology? I think the most uh, interesting pictures when we search the topology are these two pictures. As you can see, there are cups and donut, and there's a bull and a cow. Each of them have the same topological shape, but these two pictures have the different topological shape. So as you can see, the main difference between the two pictures is a hole. We can call it as a manifold when we consider this topological shape, and we can use this formula when we consider the differences between two dimension and three dimension. So let's see. Let's imagine we have two particles. If there are two particles and we are trying to move one particle into lambda 1 path and the lambda 2 path, can we make a topologically same shape the lambda 2 path to the lambda 1 path? The answer is yes. We can move this pad upward and fasten this pad and trying to move it to downward, the path is going to be lambda 1. And if we try to fasten the lambda 1 pad, there are going to be no change because if we try to fasten that path enough, there is no change in the particle's location. So that means the quantum state, that is the initial state, is the same as the particle that moves into lambda 1 path and lambda 2 path. So that is on the three dimension. And how about there are two particles on the two dimension? The story is different. Uh, if we try to move this lambda 2 path to the lambda 1 path, we cannot move this lambda 2 path to the lambda 1 path because the second particle is going to be an impedance between the two particles. That means their topological shape is different. Actually, that is a whole, as I mentioned, a manifold. So these two quantum states are different, and they're going to have the different state from the initial state. So that's why anyons already comes from the two dimension. But as you know, we are living in the three dimension. We have to restrict the dimension. So that means all anyons only exist on the two-dimension materials like graphene or nanowire or metal surface. And we can make a topologically same shape, that is the lambda 2 path to this shape. Actually, when we try to exchange their location twice, they're going to have the same representation as we move a particle into lambda 2 path. That's why on three dimension, there are two possible particles, that is fermion, that is -1, and the boson that is +1. If we try to break them twice, they're going to have no phase. And we can simply imagine this lambda 1 path as this shape. So that's that's the way to make a topological quantum computer. If we make a braiding between the two particles, they're going to experience a finite unitary set. That means we can change their quantum state by change their location. So what is the main differences between the topological quantum computer and typical quantum computers like ion or superconductor or little book atoms? Uh, It comes from how to implement gates. As I mentioned, when we want to implement a gate, we have to break their location. So that means we can make a gate that is the digital gate. But in traditional quantum computer, we can make a continuous gate that is like RZ gate or RX gate or so on. So that is the main difference. So what is the advantage of topological quantum computer? Actually, they are very strong to the error. Uh, let's imagine there is an error in the system and that is not big enough to change their excitation. So the only thing they are gonna change is gonna their locational path. So if there is an error and if that is changing their path, but if their topological shape is same, the result is gonna be same. That means even if there is a location error, we can neglect this kind of errors. Actually, that is very similar to the error correction. Uh, when you consider the error correction, if there is a locational qubit error in the system, we can compensate for this error by this error correction system. Actually, topological quantum computer is kind of hardware error correction. And the fascinating thing is, if we have an error correction code that is called surface code, actually we can make a topological quantum computer and vice versa. So how can we make this topological quantum computing? I mean, how can we define these unitary sets? As I mentioned, we can make a finite unitary set by changing their location. So let's see. To know that, we have to know characteristic of anyons first. Uh, this is the fusion law. Uh, let's imagine we have two particles and we try to move them close. And if we try to move them close, they're going to be changed into other particle. That is the fusion rule. So let's imagine we have two square anyons, and if we try to move them close, and they're going to be changed into circular anyon or other anyons or square anyon itself. So actually, this fusion rule can define all of the possible unitary sets. So let's see. To define the rule, we have to define all possible fusion particles first. So this is the M set, as I mentioned. And if there are two particles, that is A and B, if they're and their possible fusion is like this. If C particle is possible from their fusion, NABC is going to be 1. And if the fusion particle is impossible from the fusion, their result is going to be 0. We can separate this fusion group into 3 groups. The first one is vacuum fusion. Vacuum is nothing just an environment from the system. So as I mentioned, system should not be interact with the particles. Their fusion is going to be particle itself. And the second one is an abelian fusion. If we try to make a fusion and if their fusion has only one result that is C, we can call it as a abelian fusion. The last one is very important. If we try to make a fusion and if there are more than one fusion result, we can make a unitary gate set with the fusion rule. So if we don't have any non-abelian fusion, we cannot make a unitary gate set. Now let's see the Ising anyons. Ising anyon actually have the 3 particles that is environment, that means vacuum and Busan and sigma. So as I mentioned, uh, fusion to the vacuum is particle itself. And if we try to make a fusion with this Busan particle, their result is gonna be 1 or sigma. That means they are the abelian fusion. And we can notice Busan particle is an particle itself because their fusion is vacuum. And the last one is non-abelian fusion, that is sigma-sigma fusion. If we try to make a fusion with sigmas, their result can be vacuum or Busan. So keep in mind that let's make the quantum computer. So before that, we have to know what are the things we need to make a quantum computer. The first is gate. We have to change the quantum state as we want to. And the second one is computational basis. And the last one is measurement to get some information from the quantum state. So let's see a gate first. To make a gate, we have to define the quantum state first, because gate is nothing just a change of the quantum state. So we can define gate by these fusion states, sigma nx, and if the result is gonna be sigma, we can define two fusion steps. The first one, their result is gonna be one, so that is possible in this fusion set. And their final result is going to be sigma. And we can define this as a psi because it is possible from the fusion rule. And because of their fusion root is independent, so we can define they are going to have the orthogonal basis. But this is not a computational basis. I'm going to explain it later. Now we can make a fusion matrix. Uh, let's imagine we have three particles in the initial, and their result is going to be D, and their intermediate fusion is E. So what's going to be happen if we change their fusion location? Uh, the result is superposition of these states. That means we can make a unitary gate set with the formula. So but if there is no degree of freedom, I mean, if there is no choice but only one choice, we cannot make a unitary gate set because uh, it's gonna be a trivial gate that is 1 1 0 0. So the only possible way to make a unitary gate set is this fusion set. That is, we have initially have three sigma anyons, and the result is one sigma anyon. Because when we calculate the degree of freedom, there is only one possible coefficient set from the formula. The others are only one. So let's see what's going to be happening if we implement that gate. So we can have these two initial states, and their final states can be these four. So we can simply set this result as a vector matrix calculation. That is, this is the final state, and this is the initial state, and that is the matrix. So we set up the matrix. How can we define these four elements? To calculate those elements, we have to make a pentagon equation. Let's imagine we have four sigma anyons, that is more than three, and we are trying to make the same result from the same initial state. So we can change their fusion location by F matrix from here to here and here to here. And also, we can change the fusion location from here to here and here to here and here to here. They are going to have the same fusion result, but their path is different. That means we can make this equation. Uh, so we can actually uh, calculate these F elements. So because there are two degrees of freedom, that is A and C, we can make four equations. That's the result. As we calculate those elements, the result is going to be like this. Actually, that is the same as the Hadamard gate. We can use that property in the next section. There's one more thing. If we try to make a braiding, which are in the same fusion location, that is C, we can make this arm move. Uh, Actually, to calculate that, this is very similar to the pentagon equation, but this is easier to calculate because we already know this F matrix, and this R move has only orthogonal values, so we can simply get this result. And and also we don't need to consider this global phase because this is meaningless when you calculate the computational basis. So this is the same as the root z or S gates. Okay, now we knew the S gate, R gate and fusion matrix. What's gonna be happen if we break their location? So the first thing is we are trying to break their location, which are in the same fusion location. So if we do that, they're gonna have uh, R move, as I mentioned, because they're in the same fusion location. But if we try to braid them in the different location, there we need several approach. The first thing, we cannot make a braiding directly from these two different fusion locations. So we have to change their fusion location first. That is the role of this F matrix. And second, now we can braid them because they are in the same location now, like this. And the last one, because we have to change their fusion location as it was, they're gonna be F inverse, and we can get this result from this matrix. So when we try to make a braiding from these two location, the result is gonna be this matrix. Okay, now let's see the computational basis. As I mentioned, fusion space and computational basis have the different quantum basis. So if we to make n qubits, we need 2n plus 2 anyons. The reason why is the degree of freedom. Let's imagine we have 4 qubits, 4 anyons, and when we consider their fusion is gonna be vacuum, there are two possible results in this intermediate fusion space, that is A and B. So that means we can make a pair of these psi particles in the intermediate fusion because this fusion rules. That means we need 2n plus 2n anyons to make n qubits. So when we want to make these two qubits, so we can define 0, 0 as or vacuum set, and we can define 1 as 2 psi particle in the fusion space. And if we want to change the bit location, we can move this fusion result one step right away. And if we want to make 1, 1 or 1, 1, 1, 1, what we have to do is simply add them. So this is the rule. So let's see, how can we implement single gate? There are two choices when we want to make a single gate. The first one is making a braiding in the same fusion space. That can be A or B. And the second one is making a braiding between these two fusion space. So let's see the first one. If we're making a braiding in the same fusion location, that is B, they're gonna have this R move, as I mentioned, because they are in the same location. And if we calculate that, the result is gonna be root C. But it's a way more simple. We treat this as actually we are trying to make a phase gate to this B fusion state. Uh, so what we done is making a phase gate to the B fusion state. So I'm gonna use it when we try to make two cubic gates. Okay, let's see the second one. When we try to make a braiding here, they're gonna experience this step. As I mentioned, we cannot braid directly from different fusion state. We have to use this F matrix. This is a little tricky, but the result is very simple. This is the same as the root X gate, but it's more simple if we braid them twice. So when we braid them twice, their result is gonna be the flip of the fusion. I mean, if there is an intermediate fusion state, a fusion braiding, they're gonna change the two of the fusion result. So that is also true from like if we have this state and if we try to braid them, their result is gonna be psi one and so on. So this twice braiding is nothing just a flip from the two fusion space. Okay, now let's see the two cubic gate sets. If we try to making a braiding that is correspond to A or C, you might notice that is correspond to the second qubit from the A, and that is correspond to the first qubit to the C. If the C's result is psi, the first qubit is gonna be one and so on. So that means if we making a braiding into in A or C, they're gonna be root Z or S gate. Uh, and if we try to making a braiding between two fusion group, as I mentioned, they're gonna flip the fusion result. So the result is gonna be like this. So and also as I mentioned, the first two qubits is correspond to the second qubit. So this is gonna be X2 gate. How about two qubit gates? To make a two qubit gate, we have to know direction of the braiding first. If we're making a braiding into counterclockwise, they're gonna uh, they're gonna implement this R move. But if we're making a braiding into clockwise, they're gonna make R dagger. That means we can change the phase into downward and upward by change their braiding direction. So I make this as a upper phase and I made this as a downward phase. So uh, you can see uh, you can see this result. If the state is 0, 0, there are gonna be no change because there is no Poisson result. And if the result is 0, 1 or 1, 0, they're gonna uh, they're gonna cancel each other. They're gonna be canceled each other. So the result is nothing. But if the result is 1, 1, they're gonna amplify their phase change. And actually that is -1. That means if the quantum state is 1, 1, they're gonna flip their phase, and that means that is equal to the control Z gates. But you might notice there are some problems in this formula. The main problem is the possible implementations gate set is the Clifford gate set. That means we cannot implement unitary gate, universal gates. So we need a T gate or more cubic gates to implement universal gate set. And the second one is more important. We cannot even implement Clifford gate set if we have more than 2 qubits. So this is the fusion group of the uh, this is the fusion result from the 3 qubits. It's really easy to implement root X or X gate. But if you try to make a phase change from this intermediate state, it's really hard because this isn't correspond to the fusion result because even if their result is 1, they're going to have the different fusion result. So this isn't correspond to any fusion result. This makes hard to make a single Z gate or control Z gate. And actually, this paper proved that there's no possible way to make a full fusion full possible Clifford gate group. This is the number of the possible quantum results. You might notice if the qubit is one or two, the possible result is same. The number of possible result is same. But if the qubit number is more than two, it's way smaller than the possible group in the Clifford group. So that means we cannot implement all of the possible Clifford gate set. So actually, there are two solutions to make up for this problem. The first one is using an additional particle that is called alpha particle. If we use that, we can make a universal quantum set. The second one is even if we are gonna lose some potential from the topological quantum computer, we trying to use something that comes from the environment. So that means trying to use some continuous gate. So actually, the first one needs more research because there is no evidence if there is some potential hardware that can make this alpha particle. And the second one needs error correction because there we lose some potential from the topological quantum computer. We cannot protect the system from the environment. So uh, there are some problems with these Ising Anyons. But there is there is some strength from the comes from the measurement. As actually, we don't have to make some braiding if we want to use a practical particular measurement set. So let's see. If we want to measure G1 and G2 bases, what we have to do is fuse these four anion particles. As I mentioned, those fusion result is correspond to the qubits. So their result is going to be G1 and G2 measure. And if we want to make X1 and X2 measure, we don't have to make a braiding. Actually, what we have to do is change their fusion location. If we change their fusion location into here, actually there is the same as we implement F matrix to here. As I mentioned, F matrix is same as the Hadamard gate. So the result is going to be X1 and X2 measure. The last one is very fascinating. If we want to measure the parity, uh, and if we change their fusion location, the result is going to be that self. So if we measure this location, fusion location, and if the result is going to be psi, they don't have any parity because the result is the superposition of this 1, 0, and 0, 1. And if we measure them, and if their result is going to be vacuum, their result is going to be 1, 1, 1, and 0, 0 superposition. So that is a very strong point when we try to make some error correction codes. So that means we don't need any braiding when we try to make an error correction code. So that is the main approach from the Microsoft's Marinara 1. So why using Anyon? Uh, actually, the first one, there are so many papers that can realize the system on the hardware. Uh, this is the chip from the Microsoft. Actually, there is no proof that is really using Anyon, but there are so many approach. Like minor zero mode or fractional quantum Hall or also. And the second one is really easy to implement base gates. Even if the anyons have the universal quantum gate set, some anyons have very difficult, some anyons is very difficult to implement even single gates. So this is the picture of the Hadamard gate using Fibonacci anyons. It's really hard to make even single gates. Okay, let's conclude my presentation. The first, if we have a fusion law, we can define possible unitary gate set. And if we trying to use Ising Anyons, we have more than braiding because there is no suitable 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 gate set to implement universal gate. But even if that, using NU has some potential because it's really easy to implement base gates and measurement itself has some potential. Thank you for listening. Is there any question?